Welcome back to the deep dive. So today we're jumping into something that sounds, well, kind of impossible, right?
Completely paradoxical.
Exactly. We're looking at this Nobel Lecture from Steven Chu, and the whole idea is using light, which, pushes things to actually stop and trap matter.
Yeah, to hold individual atoms perfectly still.
Yep.
It's incredible work.
So our mission for this deep dive is to really get our heads around how they pulled that off.
And you'll see how this one idea, laser cooling,
Hmm.
just completely redefined everything from high-resolution measurement to, well, even microscopic biology.
All right, so let's start with the basics. The first tool in the box is what they call the scattering force, light pressure.
Right, light pressure. And this goes way back to the fundamentals of momentum.
The idea that every photon carries a tiny little bit of a punch.
A tiny punch, exactly. The lecture gives the formula, honeydew, but the key takeaway for you is just that light pushes, a tiny directional shove.
Okay, but here's the problem, right? If light only pushes atoms away, well, you can't build a trap with that.
Not at all. You'd just be blowing them all over the place. A trap needs a center, something that pulls them in.
So how on earth do you make light pull?
And that gets us to the second, more subtle tool, the dipole force.
Okay, how does that work?
What's so fascinating here is that the light's electric field, as it oscillates, it induces a temporary dipole in the particle.
Right.
And if you focus that laser beam really intensely, this force literally pulls the particle toward the brightest spot.
Wow. So the lecture had that image of the little 10-micron glass sphere just hanging there in the light.
Just suspended in midair. That's the dipole force at work.
Okay, so that holds a tiny sphere. But for individual atoms, you've got this other massive problem.
A huge problem. Atoms at room temperature are they're screaming fast. We're talking something like 10 to the 5 centimeters per second.
You have to cool them. You have to slow them way, way down first.
Which is where optical molasses comes in. I love that name.
It's a great analogy.
It really is. The technique itself is brilliant. You hit the atoms from all sides with these counter-propagating laser beams.
And you tune them just below the atom's natural resonance frequency.
Exactly. So as an atom moves towards one of the laser beams, the Doppler shift kicks in.
It pushes the frequency up.
Right into resonance.
Mm-hmm.
And boom, the atom absorbs a photon and gets a kick, slowing it down.
So it's literally like trying to run through a thick, viscous fluid.
And it worked. I mean, they slowed sodium atoms down to like 200 or 300 centimeters per second. But then came the big surprise.
What happened?
The temperature they measured, the final equilibrium temperature. It was actually colder than the theory said was even possible.
Wait, what? They built a machine based on one theory?
Yeah.
And the machine just flat out outperformed the theory?
Yeah. I mean, can you imagine being in that lab?
Yeah.
It's a scientist's dream and probably a nightmare all at once.
Because you found something completely new, but you have no idea what it is.
Precisely. They knew they had stumbled onto a much more powerful cooling mechanism that went beyond just the simple Doppler shifts.
And that breakthrough led them to this idea of polarization gradient cooling, right? Sisyphus effect.
It's the perfect name for it. The shifting polarization of the laser light creates these little potential energy hills.
Okay.
The atom is constantly forced to climb one of these hills, losing kinetic energy. But just as it gets to the top, the light shifts and the atom loses that potential energy, effectively resetting.
So it's always climbing, always losing energy, and getting colder and colder.
Exactly. And that ultra-cold precision is what made all the modern applications possible. Think atomic clocks.
Right, the atomic fountains?
Oh, absolutely. The cesium atomic fountain clock built with this was a game changer. We're talking about 100 times more accurate than what came before.
An accuracy where you lose, what, maybe 1 second in 30 million years?
Something staggering like that. But what's really amazing is how this same core idea, these focused laser beams, jumped straight into a totally different field.
You mean life sciences with the optical tweezers?
Yes. In biology, scientists now use these focused lasers to literally grab and manipulate microscopic things.
Well, like single molecules of DNA. The lecture mentioned stretching one out, right?
Yeah, stretching a single DNA molecule and watching it relax, like a tiny rubber band.
That's an unbelievable jump in scale, isn't it?
Yeah.
The same tech used to measure time to the femtosecond is also used to gently play with the building blocks of life.
It's mind-boggling, and that quest for precision, it doesn't stop.
Where's it going now?
They're using something called atom interferometry, which relies entirely on these cool, trapped atoms to measure fundamental constants with just unprecedented accuracy.
So they're taking these super cold atoms and using them to probe the very fabric of physics.
Yeah, and getting more and more accurate measurements of gravity, of everything. It's a stunning journey.
It really is. From trying to slow down some atoms to building devices that redefine our concept of time makes you wonder, what's the next fundamental limit they're going to break?